Hello students, I welcome you to EPG Pathshala. My name is Dr. Shiv Kumar Sood. I am senior scientist in the division of animal biochemistry at National Dairy Research Institute, that is NDRI, Karnal in Haryana, India. Today I will be talking about enzyme active site analysis from the paper Biostatistics and Bioinformatics. Dear students, the structural analysis of an enzyme active site begins with obtaining the three-dimensional structure file, that is PDB file, from the PDB database. Molecular structures stored in PDB files are visualized using molecular graphics applications. Otherwise, PDB file is simply a text file which has two sections. First is the header section containing the annotated information about the actual. Second section, coordinate section, which stores the coordinates of each of the atoms in the x, y and z directions. We can use an online browser containing an applet for analysis of the three-dimensional structure of the protein molecule or the enzyme molecule, or we can have better analysis with the standalone application installed on your local computer. As we have seen in the previous module, we used GSMOL and C in 3D online applications for visualizing the enzyme active site for the OSBS. PDB file can be opened with any structure analysis software, and we will be using the SwissPDBViewer, which is available freely from the Swiss Institute of Bioinformatics at the XPASI server. Therefore, we will use SwissPDBViewer because it is freely available and it is highly capable of structure analysis. Most importantly, it allows the visualization of the enzyme or the protein molecule in three-dimensional stereo vision. That is, we are able to see the depth of the molecule. So, we will be using, because while analyzing the active site, it is not that we will be using the width or the height. We would like to see the actual depth of the molecule. We would like to see at which position in the core or surface the residue is sitting, whether it is in front, within or at the back of the molecule. So, this is the application which allows the real three-dimensional visualization of the molecular structure. At the same time, it offers very good quality molecular graphics as ribbons, as ball and stick, as spheres, as solid sticks. So, this helps in switching between various forms to appreciate different properties of the molecule. For example, when we are interested in secondary structure visualization, we will be visualizing using ribbons form, where alpha helices and beta strands are viewed with ribbons. When we are interested in molecular structure, we will be using spheres for each of the atoms to be used, so that only surface atoms are shown, and various coloring schemes. For example, CPK, which will color the surface atoms at the CPK models, that is carbon as black, nitrogen as blue, oxygen as red and phosphorus as yellow. The most important component of the SwissPDBViewer is to detect the binding pocket. That is, when we have any ligand bound to the three-dimensional structure in the, let's say it's an enzyme, and the substrate is sitting in the active site, because we can have the structure with the substrate bound to the active site. So, SwissPDBViewer can detect which are the residues in the binding pocket, those which are binding the substrate or the ligand. So, this is very powerful command, and in addition, the literature information can be used to add those residues which are not detected, because catalytic residues say are not detected, and we can have information from the literature. So, by detecting the binding residues and adding the catalytic residues from the literature, we can complete the active site of the enzyme. This will help in understanding the way in which the active site is transforming the substrate into the product. After detecting the active site, we can enhance the graphics. We can enhance the graphics so that to understand, see the complete molecule in the ribbon form showing secondary structures and display the residues in the active site as solid sticks in active site of the molecule, and color the residues which are involved in binding and catalysis according to the type of the residue. Acidic as red color, basic as blue color, polar as yellow color, and gray as hydrophobic residues. We have already seen two online applications, that is JSMOL at PDB or SwissPDB and C in 3D at NCBI on-trade database. In the present module, we will be using SwissPDBViewer. We will be downloading it, installing it on your computer, and then we will be using the enzyme which is bound to the ligands. Two ligands, one is magnesium ion for its functioning and the other is OSB, orthosuccinyl benzoate, which is the product of this enzyme. This is produced from the substrate which is SHCHC. Therefore, we will use these two to actually visualize the active site of the enzyme in 3 dimensions, that is with width, height and depth of the active site. Therefore, the learning objectives in this module are to undertake protein structure analysis using SwissPDBViewer and then to appreciate the depth of the molecule in stereo vision. This will be following by the objective to detect the binding pocket residues using various commands of the SwissPDBViewer and also use literature information of the active site catalytic residues to complete the picture of the active site having a bound substrate. Finally, we will learn to enhance the graphics for appreciating the display or the complete picture of an active site on the enzyme. In the last module, we took the example of enzyme OSBS, that is orthosuccinyl benzoate synthase, to search database, that is PDB database, and found enzyme structure 1-FHV bound to its product OSB. It catalyzes the dehydration of the substrate to form product OSB. OSBS belongs to the enolase superfamily of enzymes characterized by the presence of an enolate intermediate which is generated by abstraction of the alpha proton of the carboxylate substrate. It catalyzes the dehydration reaction of the substrate, that is 2-succinyl 6-hydroxy 2,4-cyclohexadiene 1 carboxylate to produce product OSB, that is orthosuccinyl benzoate. We will carry forward the same example to analyze its active site. Visit our SwissPDB web interface to download file 1-FHV. Search for 1-FHV and in the PDB entry page, open download files drop down list and choose PDB format command. This will open a dialog box. Simply check the radio button, save file and click OK. This will save PDB file with 1-FHV.pdb as file name in the downloads folder on your local computer. This structure will be used to compute active site residues of OSBS enzyme. Download SwissPDBViewer, which is also named as Deep View and is available through Express server of Swiss Institute of Bioinformatics. Download SwissPDBViewer and unzip in a separate folder. The extracted archive of SwissPDBViewer is shown here, which has an executable file named spdb.exe, which can be run by a double click. To run SwissPDBViewer, double click spdb executable file. This will start SwissPDBViewer application and present a welcome splash screen. Read in the information and close the welcome screen. Open Prefs menu and select General command. Any command or choice or option in a menu, if it ends with 3 dots, then it conveys that this command will open a dialog box for conversation and selecting options. Selecting General command will open the dialog box for setting general preferences. In the General Preferences dialog box, check the choices you are interested in. In case you don't want to see the splash screen at startup, uncheck this checkbox. You can also uncheck the checkbox in case you are not interested in alerts when unknown groups are treated as het atom upon loading a structure. Het atoms are the atoms in the structure which are not component of the protein, but they are atoms of an external group such as a substrate, a product, a ligand, metal ion, or a cofactor. You can also uncheck the checkbox in case you are not interested in alert when some side chain atoms are missing in the PDB structure file. You can also uncheck the checkbox in case you are not interested in the reconstruction of 3D coordinates for these missing atoms. You can also uncheck the checkbox in case you are not interested in log of activities upon loading a structure. However, for now, you leave the choices as default and click OK button of this dialog box. Now, from the File menu, select first command, Open PDF file. In the Open dialog box, select one FHV PDB file and click Open. Since the checkbox for receiving alert when unknown groups are treated as het atom upon loading a structure was left checked, the general communication is received that some het atom connect requests were ignored because of probably linked to solvent, that is water molecule. Since the checkbox for receiving alert when some side chain atoms are missing upon loading a structure was also left checked, the general communication that some side chain atoms are missing upon loading a structure is received. You can also uncheck the checkbox in case you are not interested in reconstruction of 3D coordinates for these missing atoms. However, when the missing atoms in this side chain are constructed, these are shown in pink color in the control panel, which will be introduced in a short while. Since the checkbox for receiving log of activities upon loading a structure was left checked, this log of activities is displayed in a separate window. The log window shows first 3 black lines for missing atoms in aspartate 21 of chain A of OSBS enzyme. Open the control panel from menu WIND, followed by selecting the command Control Panel. This will open Control Panel window on the right side of the screen, but will cover the log file window. Therefore, adjust the size of log file window to display both Control Panel and log file windows simultaneously with blue colored molecule display window in the background of the log file window. In the last column of Control Panel, a box for ASP21 is highlighted in pink color. The black color line in the log window is clickable. Click on the line displaying missing atom for aspartate 21 of chain A. This will turn the message line to red and also select ASP21 in the control panel highlighted with red color in the first column of the control panel. Do not close the log activities text window as the same may be accessed later on from the WIND, that is wind menus command, last command. Click line displaying missing atom aspartate 21 of chain A. This will display 6 amino acids, 3 on the N terminal of ASP21 and 2 on the C terminal side of ASP21. However, to see these residues, click in the dark blue display window to view 6 residues. The 3 main graphic user interface elements are displayed now. Adjust these GUI elements by clicking in the title bar and dragging the window to position them as shown in the slide for the main window, graphic display window and control panel window. The main window has a menu bar with various menus. Below the menu bar is the toolbar which has frequently used commands. Below toolbar is a message bar showing current message in red color. The message displayed is move all. This means that when the user moves the residues in graphics display window, all residues in this molecule will move. On the left of this message, there are 2 clickable buttons. Click the first button to toggle to move selection. This means when user move residues with mouse, only the selected residues, that is the residues which is shown in red color for their labels in control panel, these selected residues of the enzyme will move in the graphics display window. This will move only selected residues. For example, when you are moving the molecule or rotating the molecule using translation and rotation commands. However, click toggle button again to move all residues for the time now. Using text command of the wind menu, switch to log file and click in the line containing message for missing atom of residue GLU127 of chain A. Click anywhere in the dark blue display. This will display the selected glutamate 127 with some other residues. However, the display is not in the center. After opening a file, by default, the selection in the toolbar is for rotation of the molecule. With the 4th button on the toolbar highlighted as black. Therefore, click on the first tool button in the toolbar to display molecule in center. The display window shows 8 amino acid residues with glutamate 127 shown in pink. In the first column of the control panel, the label GLU127 is shown in red. This conveys that glutamate 127 is a selected residue. There are 6 columns in the control panel. In the first column next to glutamate 1 to 7 in red is a small v, that is character V in the lowercase, which conveys that backbone of glutamate 127 is to be displayed in display window. Click on small v, this will erase it and simultaneously hide glutamate 1 to 7 in the display window. To display it back, click next to label glutamate 1 to 7 to mark with lowercase character V. 3 residues above glutamate 1 to 7 and 2 residues below glutamate 1 to 7 are also marked with small v in first column to convey that backbones of these residues are also to be displayed. But labels of these residues in the first column are shown in black. Therefore, these residues are not selected for performing operations on selected residues. In the second column, a small v is marked for all residues. This means that side chains are also to be shown for these residues. However, side chains of only those residues are to be shown for which backbone has been marked with small p for display. Since backbone for only 8 residues is marked with small v, therefore only side chains for these backbone residues are displayed. The third column is to display the label of the amino acid residue in the display window. However, no residue is marked with V. To display label for glutamate 1 to 7 in display window, click in the row for glutamate 1 to 7 in the third column. This will mark the residue for display of label and display the residue label in the display window. To display label for all residues, press Shift key on the keyboard and click anywhere in the third column except already marked with V. Therefore, combination of pressing Shift key with a click is used to display or hide any feature such as display label, display backbone, display side chain. This will display the label for all the displayed residues. Press Shift key and click in the third column. It will hide all the labels. Press Shift key and click anywhere in the fourth column. Open display menu from the menu bar and select second last command, render in solid 3D. This will display atoms as spheres. Press Shift key with a click in the fourth column to display the residues as solid sticks. Press Shift key with a click in the first column to unmark so as to hide all the residues. Now, no residue is displayed. However, at this stage, we can display the whole molecule in ribbon form by pressing Shift key with a click in the fifth column. This will display the ribbons, that is molecule as ribbons. However, all the ribbons appear in white color. User can set the preferences for ribbon colors from the prefs menu with selecting ribbons command. This will open the following dialog box. In this dialog box, just change the colors for the top, side and bottoms of helices, sheets and coils. Click on the color button of each of these to set the color and then select the color from the color dialog box. For coloring helices, top, side and bottom, click color button next to these. Therefore, first click color button next to top and choose light green color for the top of the helix. Similarly, color the rest of the sides of the helices. For coloring helices, use 3 different green colors. with light green for the top, dark green for the bottom and intermediate green for the side. For sheets, use pink for the bottom, red for the top and intermediate between pink and red for the side. These are boxed in the shown dialog box. For coils, use single color, that is yellow for each of the top, bottom and side. After setting the colors of each for helix, sheet and coils, click OK. After setting colors, the display of the enzyme OSBS will be shown in these colors. This coloring does not reveal a real 3D view, but only a pseudo 3D view. From this image, we can make out front and back of the molecule, but we cannot think of or measure or appreciate the exact depth. In this image, we are not able to see the depth of the molecule. Therefore, we are not able to make out whether a particular amino acid is on the front side or on the back side or in between of the molecule. The actual or 3D display is viewed in stereo vision. Open the display menu, select stereo view or press Ctrl and T. This will display two images of the same molecule. Left image is for the left eye and the right image is for the right eye. The two images are taken approximately 5-degree rotation of angle to present a different view for each of the eye. When we see each image with each eye at the same time, our brain can make the depth to see. It requires special training for eyes to view in stereo vision. Simply look at the screen images with both the eyes focused at infinity. The distance between 5.5 to 6 centimeters separated eyes and SwissPDBViewer screen shall be approximately 45 to 50. That is, the distance between the eyes and the screen is approximately 50 centimeter, and we can now see through the images without focusing eyes on the images. This is to bring both eyes in parallel, focused at infinity, instead of a point focus on the screen. This is achieved when you focus on an imaginary plane farthest away from the object you want to view in stereo. In that case, the things between the farthest imaginary plane and your eyes will appear as duplicated. One thing will appear as two things. To check this, focus your eyes at this video and go on watching. Now without stopping watching, simply bring your finger in between screen and your eyes. While still watching me in this video, you will realize two transparent fingers instead of one opaque finger when you focus your eyes on the finger. This means you focused at farther plane instead of your finger in between. Now you take away finger and focus at infinity, that is beyond the plane of these two images on the screen. The two stereo image structures shown will now appear as four structures, and the middle two structures will start coming towards each other and ultimately overlap. If you keep your eyes focused at infinity, that is in parallel, then this will make the middle two images to overlap and then show the depth of the molecule. With experience, it may take some 30 seconds to a minute to view the molecule in stereo vision. When you focus two eyes at a nearest point, say at your own nose, then both the pupils are directed towards the nose. You can see in my eyes. Both the pupils are directed onto my nose and they are in this direction. However, when you focus at a point, then these two pupils which were focused on your nose goes outside. And then you focus as I am focusing on you at this moment. Now, if at this time I focus beyond you, that is at a farthest plane, say I am trying to look at moon or sun, say moon, don't look at sun. Focus at the moon will open the pupil in such a way that both the pupil are now focusing parallelly. Now look at this at the position. Now my pupil are focusing at the farthest plane. I will show three positions of the pupil and you try to note that. First, focusing on the nose, two pupils are focusing on the nose and they are at these angles. Then on you, they open up, then at the farthest plane in parallel. When we look at the farthest plane, then the things in between will appear as two. For example, as I have tried to explain previously, that you focus on a point. For example, I am focusing on you, you focus on me. And once we focus on each other and you try to bring your finger in between without taking focus from me, don't take the focus away from me, don't focus on finger. You focus on me, bring your finger in between, you will find that two transparent fingers are appearing. They are not obstructing the focus on the screen. This happens because whenever we focus at a point, all other planes in the focus will appear as duplicated for each eye. So you try this and now you try to focus not on me but beyond me at the farthest plane, say I am at the moon. You will find I will have two images and both the images will be transparent. Try to understand this again. You focus on me, bring finger in between, without taking the focus away from me or focusing on your finger, you will find two fingers and each is transparent. Now make this finger opaque by focusing on this finger. Now when I focus on this finger, the finger is now opaque, I can see, but I cannot see what is behind the finger. And every object behind the finger is now appearing in two forms, both transparent again. So this is the way that you focus on a plane, rest of the things will be duplicated, either before or after. So focus on the farthest point so that the things in between, whatever the objects are in between, they are duplicated and they will be transparent. So try this focusing, and once you focus at the farthest plane and the objects in between are duplicated, and if we have a stereo vision objects, two images, one for each eye, then you will find that the middle two images slightly come closer to each other and overlap. Once they overlap, our brain is able to make out the depth of the molecule. So try this. This is will be learned with a little practice, and in case there is any difficulty in learning this, you please visit on the site with the previous stereo vision display. Press shift key and click in the first column of the control panel to mark all residue backbones as visible. Again press shift key and click in the second column in the control panel to display the side chains. Again press shift key and click in the fifth column of the control panel to hide ribbons, that is to mark them all ribbons as invisible. Scroll down to the last residue in the control panel, that is residue number OSB789. Select this residue OSB 789 by clicking its name, that is the label, in the first column of the control panel. The selection will be conveyed by changing the color of the label OSB 789 from black to red. This will display as shown in this slide. Now open Tools menu and select Compute Hydrogen Bonds command. Now open Display menu and select Show Only Hydrogen Bonds from Selection command. Again open Display menu and select Show Only Groups with Visible Hydrogen Bonds command. Also click on the first tool button to display the molecule in the center. Now press Shift key and click in the third column in the control panel to display labels. Now set the color of OSB 789 to cyan color as shown in the slide by clicking in the box in the sixth column of the control panel for the row OSB 789 and selecting the color cyan from the dialog box displayed. This will display the detected residues in the active site with dashed line in green color highlighting hydrogen bond to bound OSB 789 now shown in cyan color. From the literature information, we know that few hydrogen bonding or electrostatic interactions are involved in the binding of OSB to the active site. Instead, most of the interactions between OSB and the protein were reported either indirect via water molecules or through hydrophobic interactions. However, 4 residues, that is AsP161, asparagine 163, aspartate 213 and serine 262 could be detected by PDBViewer version 4.1.0 to hydrogen bond with bound OSB. This reveals the binding pocket of the enzyme OSBS. The binding pocket determines the substrate specificity. From the literature information, we also know that OSBS has a bound magnesium ion. In the control panel, mark V in the first and the fourth column next to Mg790 residue row. This will display magnesium ion as a gray color sphere. The literature information also shows that magnesium ion is octahedrally coordinated to AsP161, glutamate 190, aspartate 213 and then 2 water molecules and finally 1 oxygen of the carboxylate group of the bound ligand OSB. The aspartate 161, AsP 203 and OSB are already displayed. Therefore, mark glutamate 190 to display. The literature information also shows that lysine 133 and lysine 235 are positioned to function as acid-base catalyst in the dehydration reaction of substrate to product OSB. Therefore, mark in the first column of the control panel for lysine 133 and lysine 235 to display these residues. Hide labels of OSB and magnesium ion. Now center display by clicking first button in the toolbar. This will display as shown in this slide. Lysine 133 and lysine 235 and the bound magnesium ions are the residues involved in actual chemical catalysis. User can set the colors of the type of the side chains in the prefs menu with selecting colors command. This will open the shown dialog box for various colors according to the type of the atoms as well as amino acid side chains. Set atoms colors as CPK types. In chemistry, CPK coloring is a popular color convention for distinguishing atoms of different chemical elements in molecular models. The scheme is named after the CPK molecular models designed by chemist Robert Corey, Linus Pauling, and improved by Walter Colton. However, carbon instead of black, in original scheme CPK modeling, carbon was shown as black, but in the present example we will use white because we are using the background in the present example as black. So, set carbon as white, nitrogen as blue, oxygen as red, and other atoms like phosphorus, sulfur as yellow. For amino acid side chain colors, set as per the side chain type. For example, for acidic side chains of aspartate and glutamate, set the color as red. For basic side chains of lysine, arginine, histidine, set the color as blue. For polar side chains, set the color yellow, and for hydrophobic side chains and aromatic side chains, set the color as gray. In addition, in this dialog box, user can set the colors for displaying bonds, structures as helices, strands, and loops. And this dialog box also allows setting color for the background. After setting the colors in this dialog box, click OK. Mark V in the fourth column for OSB 789. Open color menu and select command CPK. Again open color menu and select command type. This will change the colors of the side chains of the residues according to the type of the amino acids involved. That is, red for acidic, blue for basic, yellow for polar, and gray for hydrophobic. This display reveals that 4 carboxyl groups are coordinating magnesium ion. Magnesium ion is octahedrally coordinated by aspartate 161, glutamate 190, aspartate 213, 1 oxygen from the carboxylate group of the OSB, and 2 water molecules. In addition to these residues, 2 polar groups are involved in the binding of the OSB. This display also reveals for the abstraction of a proton during acid-base catalysis, that is one by lysine, which is above the plane of the OSB, and other lysine is below the plane of the OSB. Now press the Shift key and click in the 5th column of the control panel. This will display the ribbons graphics for the enzyme molecule. This display the bound substrate with all the active site residues, side chains attached to the main chain shown as ribbon. This helps to understand the complete picture for binding of substrate in the active site of an enzyme. To appreciate binding of substrate on the whole enzyme, display all the residues as spheres for both the backbone and side chains, with the color type set as type color, that is residue type. Set the substrate color as cyan color. Now center the molecule display. Rotate the molecule to view and to find out the cyan colored substrate. After we rotate and reach the position shown in this slide, it reveals the binding of the OSB in the active site of the enzyme. This shows that the OSB is bound in a cleft on the surface of the enzyme and reveals that most of the surface has hydrophilic residues colored with red for acidic, blue for basic, and yellow for polar residues. Cyan colored substrate is bound within a cleft on the surface between 2 lobes of the enzyme. In the protein structure module number 11, we have already seen that the most of the surface of the protein is hydrophilic and interior is hydrophobic, and all the functional sites, maybe active site of enzyme or binding site of a receptor, they are present within the clefts, maybe formed by two lobes of the same domain or two domains of the same subunit. Therefore, this now shows that the active site is actually present on the surface within the cleft and is hydrophilic, having residues which are having mobility for their functioning, that is transformation of the substrate to the product. Dear students, in this module, we learned about analyzing an active site of an enzyme using SwissPDBViewer and PDB structure. The display of the three-dimensional structure was appreciated with the visualization of the depth of the molecule in stereo vision. Because without stereo vision, we can't see the depth, and depth is the one which allows us to actually appreciate the real object, such as appreciating a real scene. Distinguish it from a photograph. For example, let's say you have a photograph. You can say, okay, something is in front and something is at the back, but you cannot tell what is the distance between these two planes. You cannot appreciate the depth. Without appreciating the depth of active site or a protein molecule, it will not help to understand the mechanism of the enzyme. Therefore, try to learn stereo vision. Then we learned in this how to detect, in this module, how to detect the active site binding residues. This helped us to complete the picture with addition of the literature information, so that then we were able to appreciate the real total complete active site in 3 dimensions, real 3 dimensions, with the depth also shown in addition to width and height. Then we also enhanced the graphics, which helped us to understand, the mechanism, that is the path which is to be taken by an enzyme for converting a substrate into a product. Therefore, with this power now, having SwissPDBViewer in your hand, try analyzing other enzymes and try to understand what may be the mechanism by which this enzyme in your hand actually works. I thank you all for visiting EPG Pathshala.